Hey, welcome back to creating a NES emulator from scratch using Python. My name is Andy, and today we're going to continue working on the CPU part of this emulator. So for those of you who are watching for the first time or are catching up on YouTube, what we're doing is creating a working Nintendo Entertainment System emulator. At the moment we're working through doing all the instructions on the CPU, as well as the CPU and the memory and all that kind of stuff in general. So basically we're just going to continue doing what we've been doing. Last week we left off working on the PHP instruction, which is a stack instruction, so pushing things to the stack, in particular the processor status. And we got to the point where that wasn't really working for us. So let's keep working on that and see what happens. So I believe if I run the test ROM, so what we did last week was created something that could load in a NES test ROM, and also compare it to a log of expected input, and we wrote a regex parser that could compare it to the known output, and now we're validating that what our results are what they're expected to be. And so we've kind of hit a point where they're not, so now we've got to figure out why they're not. Cool. So why are they not? So it's after a PLA that they're not. So let's go look at a PLA, which is pull the accumulator. Interesting. So let's put a breakpoint there and let's see what happens. So what doesn't match up? Our P doesn't match and our A doesn't match. So what is our soft.expected A? So this is our A register, which is our arithmetic, or maybe not arithmetic, arithmetic register or something. What you do, you kind of adds and subtracts and multiplies and all that kind of stuff. CPU.areg. So let's compare. The expected A value is 127 and the A value that we actually have is 111. So what is this instruction that we're actually doing? Is PLA. So we're pulling from the accumulator. We're pulling to the accumulator. So we're setting the accumulator, and then the accumulator is not the value that we expect. Right, so why would that be? Now, another thing that might have to do with it is the fact that our P match is also wrong. So let's look at our expected P, 109, and let's look at our, so our P is our status reg. So we're getting our status reg is also different, ever so slightly. And just looking at it here, it looks like the second lowest bit is set when it shouldn't be. So yeah, that's correct. Now what's the second lowest bit of our status instructions? It's got to be Z. Yeah. So basically what we're saying is that the last instruction should have executed and equaled 0. If the last operation resulted in a 0 value. So this is being set to 1 when it shouldn't be. So basically the last operation ended in a 0 value and it should not have. And the value in our areg is wrong. So let's look at what we've done. So we've pushed the processor thing to the stack, and then we've pulled that value, presumably. So what these stack instructions are doing is going to be pulling and popping. So it's going to add a single byte to the stack, and then a pull is going to pull a single byte from the stack. So we do a PHP and then a PLA. So the PHP should push the processor status to the stack, and the processor status should then exist on the stack, which is 06F. So let's see what that equals. 111. and then that's being pulled to the A reg, yeah, which is 111. So it looks like it's working how we expected, so that we've pushed the processor status and then we're popping that off and putting it into the A reg. The real question is why this thing is different. So let's open up the NES test log, start doing some thinking. Right, so we've got a PHP, and then we've got a PLA. And so we're saying after the PLA, the A reg should be 7F, which if I had to guess would equal 127. Yeah. So we think that it should equal 127. So why do we think that? 7F. So the fact that this is 7F instead of 6F makes me think that maybe we're... Let's look at both these values in binary. Potentially we're flipping a bit or something. Yeah. So this, so 1, 2, 3, 4, 5. So the 5th bit is being flipped. Which is going to be 1, 2, 3, 4, 5. So this useless bit used by the stack copy. Yeah, right. So this is what it's going to be. So let's find wherever I found this table. I get the feeling that I found it on the NES wiki, which is a useful resource that we use to kind of check up this kind of stuff. So let's look at the CPU for the NES, and then let's hit up the status flag behavior. Perfect. Seen it below. So there are 6 and only 6 flags. Yeah, B flags, whatever. 2 instructions, PLP. Oh, here we go. 2 instructions push the flags to the stack, PHP and break. In the byte push, bit 5 is always set to 1, and bit 4 is 1 if from an instruction, or 0 if from an interrupt line. This is the only time where the B flag actually exists, but not in the status register itself, but in the bit 4 of the copy that is written to the stack. Right. So these 2 useless bits are actually used when we're copying things to the stack. Yeah, so let's set bit 4 and 5 of PHP, when we're pushing to the stack, so when we do a PHP, so let's find out PHP. Oops, not in there, in here. So the PHP is going to be pushing this data to the stack. Now this is going to return and we actually just want to make sure that we binary and this with the correct bytes that we want. So 0th byte, 1st byte, 2nd, 3rd, 4th and 5th. So set bit to be 1, and then I'm just going to reference this thing. So when we run this now, basically we are setting the status reg to be pushed to the stack, so using PHP, but we're also going to be enabling bits 4 and 5, and that's just going to make our lives easier in the future, where we don't have to worry about coming back to this. We'll have to do this again when we're looking at breaks, IRQs, and NMIs, but for now, we just set these 2 bits. So I think this should work now. So what, did that help at all? A match, nope. So now our CPU reg is 32. Oh, I shouldn't have ANDed that. I should have ORed that. So we want these always to be set. That's my bad. Yeah, so now the areg matches. We're still at the same point. The preg still doesn't match, but that's fine. That's a separate problem. So the preg doesn't match. So why doesn't the preg match? So let's go back to that. So our expected P versus our actual P. Yes, so it's as 0 byte is being set versus not being set. So the actual thing that we expect is that it equals 0, and that, which means that the last operation did not result in a 0. So that's what we had. What is meant to have happened is that the last operation did not result in a 0. Whereas this thing is saying that it did result in a 0. So I guess the other thing is going to be to look at PHP and see which flags it's meant to set. Yeah, so push status register implied, and it's not meant to change any of these things. Ah, but PLA does. Okay, so this is why we've gone wrong. So each of these things is going to have a different set of attributes that it modifies, of status registers that it modifies. Right, so let's look at this. So a stack pull is not necessarily always going to set nothing, and a stack push is going to do something separate. So let's get rid of these, and then we'll have to do it on a instruction by instruction basis. So let's find usages of this. There should be 3. So we've got 3 stack push operations, and what we're saying is PHP is going to set nothing. So what this is saying is that none of the status registers of the CPU are going to be set by this instruction. So it's not going to modify anything, which is handy. Yeah, right. So let's keep going then, and then a PHA is going to do nothing, and a TXS is going to do something, which is going to push it to the stack. Yep. But this is actually going to change N and Z. Yep. And what this means is that the sets negative bit is going to be true, and the sets 0 bit is going to be true. So we're setting these to true, and says based on the result of this instruction, we want to set the negative bit or we want to set the 0 bit. Cool. Let's keep going then. So PLP, does this do anything? So PLP actually sets the stack. So we don't actually need to do anything there. PLA. So it's going to overwrite whatever's on the stack, so it doesn't matter what we set. So I'm just going to write that. PLP sets the stack. PLA is going to write the N and the Z bit, so much like a TXS instruction. And then a TSX instruction. Let's find out what this does. Is again going to set these first 2 bytes. which is negative and 0. Cool. So now when we run this, the preg should be fine. Yeah, so we made it past that instruction. So we made it past the PLA, but now we're doing other stuff here. Unsupported operand for types, none types, and for int. Yeah, so value is none. Okay, so the value that has been returned is none. So let's set a value here for when value is none. Let's work our way up the stack and see where this has come from. So the value is none. What's our instruction? Is a PLA. So what is the PLA instruction that we are looking at? PLA. So what does PLA stand for? Pull accumulator. So it wants to pull the value and shove it into the accumulator. So we want to set the areg to be pulled data. Yep. And the write function should decrease the stack size, get the pulled data, and then write the pulled data to the areg. So that seems like what I would expect. Right. So let's just set a breakpoint here for when class.name, so when PLA is in class.name. So let's look at the PLA instruction. Let's just step through and see what happens. So we get a memory address of none because we have immediate or implicit addressing, so there's actually no memory address that we're trying to find. We get a value of none, which is kind of what we expect because we're not actually going to be pulling anything from memory. Updated value should also be none, but we should have done our write. And then cpu.apply side effects, return the value. Right. So this self.statusreg.update, because we're trying to set the negative bit off a 0 value. So what should this set the thing off? Probably the value of A is what we're saying. So the problem here is that this instruction wants to set the negative bit and set the 0 bit, but it doesn't know what to set it off. So if we just return cpu.areg, it'll set off whatever's in the areg. Yeah, which would be what we want it to do, I would think. Cool, alright, we made it way further, one instruction further. Instruction not found, C9. Alright, so it looks like these are working now. My only thought is, are there any pushes that write this? Well, let's look, I've got them all here. Push. So a TXS, so data to push is going to be cpu.xreg. So we want to set this negative and this 0 presumably based on the value that we are pushing. So I'm just going to return data to push here. Alright, let's do that again. So let's just check out all these things. Instruction not found, C9. So we've made it to the next instruction. So C9, where's 9? Compare. Right, so compare with accumulator. Let's look it up here. So we've got to compare with accumulator and it affects the 3 flags. So let's go to our base instructions and let's write a compare class. So a compare instruction is presumably going to compare the given value with the accumulator. And it's going to set the the negative, the 0, and the... What is the C bit? C. I don't know what C stands for. Carry. One if the last addition or shift resulted in a carry, or if last subtraction resulted in no borrow. So presumably this is going to be something that we're going to have to figure out later. Because I'm probably not doing it right now, but... So let's say it sets the negative bit is true, it sets the 0 bit, and it's also going to set the carry bit. Is going to equal true. Now this sets carry bit attribute probably doesn't exist yet, so let's just add it in here. Sets carry but is a common typo I seem to be doing. Sets the carry bit. Cool. So what is this thing going to do? Compare the given value with the accumulator. Here we go. So compare sets flags if the subtraction has been carried out. If the value of the accumulator is equal or greater than the compared value, the carry will be set. Yep. The equal and sign flags will be set based on the equality of lack thereof and the sign of the accumulator. Okay. So let's think about that for a second. So is this going to be compare accumulator versus compare x? So compare is going to be something that we do pretty regularly by the looks of it. CMP. My thought is that we should probably have a generic compare instruction instead of specifically CMP. So let's do compare. Well, let's start with CMP and then we'll try and do it. So what are the functions that we can overwrite? So it's going to have different types of addressing, and then instead of writing things, we're going to be writing things, I presume, or applying side effects. No. So do we have anything? So bit instruction is going to be similar, which is going to set the status reg, and an AND instruction is going to be very similar. So let's look at how we've implemented AND. So the AND instruction is bitwise AND with accumulator and store result. The compare is going to be compare given value with the accumulator. Now, do we store this result anywhere? No, we don't. We just compare and then we set the bytes. And there's going to be lots of different things that happen here. So if we look at the NES test log and find the CMP, what we kind of should be able to see is that nothing should really change in the areg, xreg. Yeah, the only thing that should change is the status reg. Yeah, which is what has happened. So it's just going to change the status regs. Cool. So the value we will get from the addressing, and then we'll get it passed into the write instruction. So let's go back to base instruction. And let's go. So instead of ANDing the CPU areg, we want to compare given value with memory. So compare sets flags as if a subtraction had been carried out. So we actually want to do a subtraction, but then we want to throw away the result, but we want to set the flags. So which one do we minus from each other? If the value in the accumulator is equal or greater than the compared value, the equal in the setback. So I think we're going to want to do compared minus the accumulator. And I think that's all we need to do. We just need to do the value minus CPU.areg. So this is going to not actually do a minus. It's not going to change the value of the areg, but the value that we return here, we're going to set the negative bit, the 0 bit, and the carry bit on. So I think this is all we need to do for a compare. And I think the different things like CMP versus CPS versus CPY will be all the same. They will just need to have a different value for here for areg versus yreg versus xreg. So let's start with CMP. And let's implement some instructions of this. So they're not stored, they're not jumps, loads. I'm going to call these arithmetic instructions, for the lack of a better word. So let's get something. And if I go back to here, I'll be able to see which modes I need to use. And there's a lot of them. So yeah, let's do this. So we need an immediate one. So we need CMP immediate, which is going to use immediate addressing. Immediate addressing. I always forget what this is called. Immediate read addressing. And it's also going to inherit from CMP. So it's a compare instruction that uses immediate read addressing, and the identifier bytes are going to equal bytes 0xC9. Now, here's an interesting kind of thought. What if we didn't specify identifier bytes? There'd be none. I kind of want to make that a property that we need to implement. So make this class abstract, but we'll kind of come back and do that. Actually, well, let's do it now. ABC. So I forget. I think we can just make this inherit from ABC now. And the answer is, let's look up Python 3 abstract classes. So the answer is Python 3 has changed how abstract classes work. They used to be a bit dodgy in Python 2, with the way you had to declare them using meta and stuff. Yeah, okay, so meta class equals ABC meta. Is there a nicer way of declaring these? Potentially not. Yeah, there we go. So you can just inherit from ABC and then call abstract method. I wonder if you can have abstract properties. So can we have abstract methods? Yep. about an abstract property? There we go. We can indeed. And then I think we'll just need to do def identifier byte class return none. And the answer is we not only want to make this an abstract property, but we want to make this a class method. Yeah. Let's see if that works. Yep. And then now if I do, I'll just have to import this new instructions file, which is arithmetic instructions. Now if I take this out, it should throw an error saying you haven't implemented this correctly, which it hasn't. So that's kind of shit. But yeah, let's find this out then. Python 3 abstract class property. Until Python 3.3, but I'm using Python 3.3. Since 3.3, abstract property is deprecated in favor of the way that this guy's used it, which is app property abstract method. Okay. And it's a class method. Property abstract method. So let's do Python 3 class properties. So let's see how we can create a class property. Class property. Yep, properties. Class methods. I kind of want a class property though. Using property on class methods. Here we go. A property is created in a class per effects. So if you want a class method property, create the property on the meta class. Oh god. Okay. Scratch all this. I'll come back and fix this out some other day. Undo all the way back to the start of history. Good enough. Alright. So back to our arithmetic instructions. So we set this as C9. And now we should find our C9 instruction, which works and gives us the value that we expect, which is awesome. So let's implement all the other different types of these things here. Oops. So what else we got? Zero page, absolute, indirect. I kind of just want to write something that will generate this code for me based on the different types. This would be really funky, but kind of fun. So if we did something where we can enter this kind of format and then have it spit out the actual classes, that would be really cool. Python this is only going to really work where we have no methods here. So I kind of wanted to generate the code. Let's see if there's anything. That seems cool. So class factory, the argnames variable, yada yada yada. So special class equals class factory, call it special class, and there's your options. Ooh, that seems pretty cool. Yeah, we could also just do this. Type. So we could, more methods can be put in subclass. Would be pretty cool to spit out something like that. Because I don't really want to declare it that way. Do I? Because if I had a list here of which classes, which things I want to use, which addressing types I want to use, I could just declare them a la this. Name equals special class. So I could declare them like this, where I said CMP immediate, which is going to inherit from these things, and the identifier bytes is going to equal this. So if I do this, I get rid of this. Can Python still find this? It can. Oh, that's pretty cool. So if I wanted to just spit out lots of classes like this, so let's do CMP. So this is why I kind of want to do it with classes, because we can start doing a lot of this kind of stuff. So CMP addressing types is going to equal, so we actually just want to read in this string, right? So this is only going to work for things where we don't need to define any of the methods. We don't need to overwrite. So like for instance, you know, if I look at load instructions, these are all going to be fine. We could generate all of them, but something along the lines of bit instructions where we need to overwrite some methods, we'll probably need to write them. But yeah, all of this stuff can be automatically generated, and this would be pretty cool. What I really want to do is have it literally read in this kind of structure, which is the structure that we get off this 6502 website, and then have it be able to generate all of them. That'd be pretty cool. So we don't care about any of this crap. We literally just care about the fact that it's associated with CMP and these kind of things at the start here. So if we just split on space, So let's do this. So we have a string here, which is going to define this, and then we can say, so when we load this file in, this code is going to get executed. So we have to be careful that we're only loading this file in once, but whatever. We want to dynamically declare some classes. So for CMP type in compare types, we dot. So we want to split it based on the lines, and then for each one of these things in here, for each line we want to split that line again. So for each line in this, line for, so we're doing a list comprehension. So we split it by lines, and then we also want to just split it by spaces and get the first element. So let's see if this gets what we expect. So what is CMP type? Immediate, yep. And then CMP, which is not what we want. So we kind of just want it to return the word immediate and then to return this. So this is probably going to have to split on a new line. So what if I do this? Alright, what does compare type.split return me? And what does compare type.split without anything here return me? Yeah, really splits it, hey. Alright, so we want to split on new lines, but we don't actually want this first or this last one here. So if line does not equal a blank thing. So what's our compare type now? Immediate. Yep, and then it should go on to 0 page, so on. So forth, all the way down to indirect x, indirect y, and then nothing. Perfect, okay. So we've got the first word. So let's create a set of mappings that's going to map these types into things that we know. Do I have a helpers function? I do. So def description to addressing. So it's going to take in a description. Turns a string description into a addressing type. So we just kind of want to return immediate, and this is going to be based on the format from this site. There we go. So immediate is going to return immediate addressing. So immediate read addressing is what I called it. So this is going to be an addressing type. So we know that this is going to return an addressing type, which is pretty cool. What was the other things that we saw here? So we've got 0 page is going to go to 0 page addressing. Zero page X. I think it's called 0 page with X addressing. Alright, let's open up addressing and find 0 page addressing with X. Also helps me not have to remember these class names because I'm terrible at doing these. Absolute is going to be absolute addressing, absolute X, so on, so forth. This is going to be the same, but it's going to return Y. Then this indirect X is going to return indirect addressing with X. And then this thing is going to return indirect addressing with Y. Now there's going to be more that I haven't put in here, but for now, that's all the ones I'll put in. So we declare our array and then we want to get description. So we do want this to error it out if it can't find it. Cool. Yeah, so this is going to return an addressing type. So now when we come back to arithmetic instructions, so if we declare our CMP types, for CMP types in this, we want to print CMP type, we want to print description to addressing of the CMP type. So when we do that, what does this return? Immediate read addressing. Sweet. So what we want it to do is then to declare a type of immediate read addressing. Do we really care what it's called? Not really. Not really at all. But we need to call it something, which is going to be of type addressing and of compare, and the identifier bytes is going to be this thing. So really what we want is just to say, let's get each line. So CMP entry, and then now that we've got CMP entry, let's split that based on, yeah, just split. So data equals CMP entry dot split. So addressing name is going to equal data 0. Type name is going to equal data 1 plus data 0. So in this case it's going to be CMP immediate. And then the next thing will be C9. Now, is there a thing where this formatting is different? Yeah, it is. So we want to find the opcode here. Which sometimes might have something, sometimes might not. But thanks to our old friend regex, we can probably find. Oh god. Kill me, regex. Kill me. Alright, let's find our regex. So where's that pattern here? So RE. So let's find regex. Regex dot match pattern and then string. So the pattern is just going to be find any amount of word characters. Let's go back to regex 101. Our friend in the fridge. So word, a single character, any non-white space slash W. Word. Any amount of word, then any amount of white space. And then we want any amount of words. And then a fixed amount of characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then any amount of words. And then whatever, we don't care about the rest. Dot slash. Cool. So this is going to be our pattern. So we want to match the pattern against CMP types. And then I believe wherever I was doing that, get that into matches and then matches.group. So matches equals that, matches.group 0, 1. Okay, so let's see if matches.group 1 is what we expect. It is not. Matches.group 2, line.strip. CMP type, we want to compare it to, right? CMP entry. Okay, so matches group 1 is immediate, group 2 is CMP, and group 3 is going to be our thing. Okay, so addressing is going to be group 1. The class name is going to be matches.group2 plus the addressing string, which is matches.group1. And the bytes are going to be C9. So can I just get a hex of C9? String object. Okay, so can I get an int base 16 of this 201, which is 0xC9 201. Right. Int matches 3 16 matches dot group 3. Okay, so now we're taking. Alright, well, let's see what we got. So now, hypothetically, we should have every one of these types of compares available. So let's go down to somewhere in here, breakpoint, and let's look at our instructions. Okay, invalid literal with per. So evidently we're doing something wrong. C9, C5, per. So 0 page is breaking us. What's that compare entry here? 0 page X. Okay, so this should be, instead of any white space character, should be anything that's not white. Instead of any character, anything that's not white space. So now 0 page X should still work. Yep. Okay, cool. Can't find index Y, yep. So now, self.instructions. So we should have all these normal classes that we created. And then down the bottom, or somewhere, do we import this file? 67. Do. 75. Yeah, so now where do these things exist? Here we go. CMP immediate, CMP immediate. So now we have things that do. I want this to be called class name. I'm going to set the identifier byte, addressing and type CMP. So we should have 75 things here again. Yeah, so here's all our CMPs. CMP indirect X, CMP 0 page. Yeah, okay. That's pretty cool. Okay. So now we have something that can create. So this is kind of why I wanted originally. I wanted to get a hang for doing all the other stuff, but this is why originally I wanted to do it this way, was that we can now just paste in a list like this and we can get out all the classes just based on having defined the addressing type and having defined the base compare instruction and being able to set things like sets, negative bit, yada yada. And now it'll just automatically do it all for us. Now this function here, now interestingly, if we get rid of this, what if we did A equals this? Are these things still going to be registered, or do they need to be stored somewhere? 68, they actually need to be stored. Okay. So we kind of want to move this function to the helpers. So we want to create classes from string. Class string is going to be a string. From descriptor, and based on format from here, So for class entry in each one of this class string, here's the pattern. So we can just compile this pattern. How do we do this? So here's your pattern, compiled equals that. We don't want to import typing from RE. We just want to import RE. It's probably one of the worst features about Python 3. Alright, and then down here, compile pattern.match. So compiled class pattern.match to the CMP entry, to the class entry. Yep, addressing is going to be the thing we get out of it, the class name we're going to build, and then we just want to yield type of yada yada, and the actual only thing we need to pass in is the class type. Which would be compare in our example. Cool, create classes from string. I'm going to call this generate. So back here, we can now do for generated in generate classes from string of the compare type with the compare type string. Get this from helpers. Cool, so now declaring our all our compare types, all we need. So where is our base instruction thing? So it's probably best if we pull this up here now. So here's our compare type. And then, yep. And then all we will need to do is, it's just this. So for generated in generate class from strings, types.append generated. Now we're getting funky. So basically, now we're going to generate all the CMP classes. So if I do this, we should have all our CMP classes still in here, somewhere down here. Yep. Now the real question is whether we can have things like brackets in the name, which I don't know. So I'm going to say back in this helpers method, what we should do is we should say the class name is going to be these things, and we're just going to strip it of commas and other stuff. So Python strip of cars. Yep, so probably easiest to do it like this. Line.translate. Yeah, whatever. Class name. So let's just get rid of that. And then we basically just want to sub out anything that's in brackets or a comma. So now when we create this, yeah, CMP in direct 0, CMP 0 phase, CMP, yada, yada, yada. Alright, cool. So that's pretty dodgy, but pretty cool. So I kind of want to do CMP there, and then I can just do CMP types. Yeah, so now I have CMP all done. So let's do this for our load instructions. So load A immediate. So where's our base instructions? Load. Load A, load X, load Y. So let's copy all of these to our load instructions. Let's cut that crap out. Yeah. Okay, so load A, for instance, is going to take this kind of stuff. So let's do load A's. So load A types is going to equal this kind of stuff. Let's just put it back here. And then we just need to do this. We need to have a types at the top of the file. Generate classes from strings, and we want to do it for LDA types. And all these LDAs can just disappear now. Now do we have LDAs in here still? LDA immediate, yep, it's working as expected. Sweet, alright, let's do the same thing for LDX. So what are our LDX types? These things. So generate LDX. Yep. And then let's do the same thing for LDYs. LDY and LDY types. Load Ys, okay. And now all this code can go. Now the real question is, do I actually want these? I kind of like having these in the base class. Let's get them out of here and let's just have these files be these weird declaration things. So let's import these. Same thing with here, let's put this back. Nice. Okay. Done. Missing 0 page Y. Mm-hmm. 0 page Y. Whoa. Anything else? No. Done. PHP, CMP immediate. Now we're down here. Yep. Alright, that worked. So let's keep going then. Let's keep converting everything to this new Arduino. Now, it might take pretty much just as much space, but the reality is it's going to be a lot quicker when I want to add, a lot of CMPs or a lot of something else to do all the addressing types. Yep, so all these AND instructions can go. So let's do that. So these ones are going to have to stick around, bit instructions, whatever, they can stick around. But AND instructions? Hell no. So AND types. And the only thing we need to find is and we just need to copy all this across. And we're done. So all these can go. We can get rid of all that shit. Yep. Cool. Alright, so that's bit instructions, arithmetic instructions, generic instructions. So these, since these need additional data, I'm not going to bother doing them. Jump instructions, it's probably worth doing these. Kind of, not really. They're a little bit different since I've already done them. Load instructions I've done, store instructions, it's definitely worth doing these. Alright, so let's get this. So store X types. Ah, hey Blacksteels, welcome. I'm just doing some generation of instruction types from documentation strings because I'm bored of typing things out. I kind of want to be able to generate these things. So now we can just copy the documentation. So we know that these are all the S to X types. So 0 page absolute, and it will parse that string and create a new type based on the fact that we know it's an STX 0 page addressing and it's got a byte identifier byte of 86. Cool. So all of this can go. So store A can all go. And then store Y can all go. And let's find STY. Right, rock on. So this should all still work. Yep, cool. So we're now generating all our required classes just based off this string stuff. And all we need to define is the addressing stuff, which we've defined once, which is now all done automatically. The only thing we need to define to get all these like 6 different types of STAs is this STA class, and this is all the STA class is. Inherits some rights to memory from instruction, and just sets the areg. Cool, alright. So what are we up to? We need a BEQ, is that right? We should still have 75 things here, yep. Instruction results not expected. Right, so we actually aren't expecting instruction results of the BEQ. So we've got a BEQ. Must be in jump instructions. BEQ. Yep. And we're not what we expect. Right, okay, so what's different? So the P match is false. Yep, so let's check. What's our expected P versus what's our actual P? Using that. See how far off they are, yada yada. 102, so our least significant bit isn't set. If we look at status, the least significant bit is the carry bit. And the reason that this is wrong is because we haven't implemented our carry logic here, which I forgot to do. So if we set the carry bit, then let's do carry. We want it to be a bool of, when is the carry bit set? Oh, no, not this one. I appear to have. No, we've got this one. Right. So if I go to compare, so compare sets flags if subtraction has been carried out. If the value in the accumulator is equal or greater than to the compared value, the equal and sign flags will be set based on the quality or lack thereof and the sign of the accumulator. If the value in the accumulator is greater than, is equal or greater, so we do, so where's our compare instruction? It's actually the compare instruction that's going wrong, which is going to be an arithmetic instruction, I presume. Yep, so compare. So value minus the areg. So if the value in the accumulator is greater, equal or greater than the compared value, so if this is bigger than this is going to be 0 or less than 0, the carry will be set. So if it's less than or equal to 0, the carry will be set. Value less than or equal to 0. Yeah, the equal and sign flags will be set based on the equality or lack thereof and the sign of the accumulator. The accumulator isn't updated though, is it? Well, let's presume that it's not for now. Yep, so we've got past that point, and now it's a PLP or something that's broken. All right, so what's wrong here? So our P match is wrong again. All right. Alrighty then. And if our P match is wrong, 239 versus 21845. Alright, so I'm willing to bet that that's probably not what we want. Let's see. Alright, let's put these both in a binary and let's see what they are going to equal. Holy shit. That status reg equals like 1 billion. That seems wrong. I'm just going to put it out there. Alright, so what have we just done? We just did a PLP. PLP. Alright. Let's go. So, implicit addressing, stack pull. Right, so PLP is going to set the stack. So is this the first PLP that we've come across? Yeah, this is it. Sets the stack. Wait, PLP? Is the PLP meant to set the stack? What the hell's a PLP meant to do? Pull processor status from stack. Right, so we're calling from int. Yeah, so this function is wrong, clearly. Alright. So what is key? Yep. So the carry is going to be value 255. So what's the bin of value? Is going to be the maximum thing. It's going to be 1 for everything. And then what is 1 shifted by I? Is going to be 1. So this is going to be 1. Right, so then this is going to equal 2. Alright, so we actually just want this to be the bool of this. Right. So what we're saying is the bool of this is either going to be 1 or 0. So it's true. Yep. And it doesn't match because we thought everything should equal 1 when in reality there should be a single 0. So why should there be a single 0? So the PLP is going to push PHA. What the hell does PHA do? Push accumulator onto stack. The accumulator's got a value of 255, but when it gets pushed to the thing, we've got to remember that some of these bits are set in a weird way. So our thing works correctly now. So let's look at PHA. Oh, really? There's no information on it. Over here, okay. So there are 6. There is no B flag. Push the flags to the stack. Two instructions, PLP and RTI, pull a byte from the stack and set all the flags. They ignore bits 5 and 4. Right. So bits 5 and 4 in a PLP are actually the thing that gets ignored. But interestingly, so we push this to the stack. Oh yeah, and the stack does actually equal 0xFF now. Whereas what we want it to equal. Let's open up our NES test. Let's go up to the top. PLP. Yep, this is where we are. We actually want this stack to equal FB. And which one of these bytes is not set? 0, 1, 2, 3, 4. So the fourth byte should not be pushed onto the stack. PHA. So even though A is FF here, when we push it, the stack should just equal... Oh, not the stack pointer. Wait, what the hell does PHA do? So PHA, push accumulator onto stack. So the accumulator equals FF. Then we're pushing the accumulator onto the stack. So the stack pointer's moved up, but why does it equal AD? Alright, it's just on the stack, and then PLP is going to pull from the stack, right? So the value on the stack is probably FF, but then when we do a PLP, it actually just loads EF, which is going to be this, so it's not going to have the fourth bit set. Okay, so it is PLP's problem. So two instructions pull a byte, they ignore bits 5 and 4. What was the other one? PLP and RTI. Oop. Do I have RTI? Nope. PLP. Alright. Let's hit up PLP. Ignores bits 5 and 4. Or 4 and 5. So this from int function, we actually just want it to ignore bits 4 and 5. So what are the ways to do that? To pull data, we want to set it, but we just don't want it to modify bits 4 and 5. So let's just pass through a list of ignores. 4 and 5. And bits to ignore, which is going to be a list of ints. Cool. If I is in bits to ignore, then continue, which will just go to the next entry. Right, so now that should work. Yeah, so we've got even further. Well, we're getting pretty far in now. Instruction not found. 09. Alright, let's keep going then. 09. 09. ORA. Which presumably is OR with A. What do you know? Okay, so what flags does it set as those flags? So let's find our base instructions. This is very similar to an AND. This compare thing we'll have to make generic, but anyway. Class OR, which is an instruction. And it's going to be very similar to this, bitwise OR, and store the result. And it's going to store the result in the accumulator, and it's going to update the N and the Z flag. So it's almost going to be the same as this, but this is going to be an OR. Right, so let's find the implementations of this. Yep, so this is in bit instructions. I actually think this should probably not be in bit instructions. It should be in arithmetic instructions. Yep, and I think bit instructions. I think that these should also be. Cool. So I'll put these at the top, and then I'll start generating stuff. So this is the AND instructions, and then I also want OR instructions. So now to implement all the OR types, all I need to do is implement OR, which I just did, and I just need to copy across this string, and all the classes will be generated for me through the magic of magicness. Done. OR. Did that not work? Oh no, we just got way further. Way further. Oh my god. Instruction not found 4.9. Alright. That was all the ORs. We're speeding up. What is it? 4.9. EOR. Exclusive OR. What the hell? So it's not. So exclusive OR means if they're the same, it's actually not true. Alright. Let's see if there's an exclusive OR bitwise operation, and if not, we'll just have to implement. Da, da, da. The XOR operation on two booleans. So A and not B, or B and not A. Yeah, I'm just going to do that, or something like this. So let's implement a base instructions. Let's go to OR, and let's implement EOR. Exclusive OR. I don't know enough if it's bitwise at this point. Oh no, it is. It is a bitwise exclusive OR. Yep, so it's the same things. So we have a value. Python bitwise exclusive OR. Da, da, da. Each bit is the same as the corresponding if that bit is 0, and it's the complement of the bit if that bit is in 1. So I think that's it, right? Done. So let's go back to here, and let's do EORs. EOR types. And where are my types here? So this is another 8 instructions implemented, which is pretty cool. Alright, so that's all my EORs done. 6.9, not found. 6.9 ADC. Add with carry. Effects flags, a lot of frickin' flags. Alright, so this is we're gonna get a bit more interesting again. So we've got our ADC. It's going to set a lot of flags. It's going to set the negative bit, it's going to set the 0 bit, it's going to set the carry bit, and it's going to set the overflow bit. Alright, cool. And what do we want it to do? Add memory to accumulator with carry. So A, add memory to accumulator. Right, so we want to add a value from memory, we want to add whatever's in the accumulator, and we want to add the carry. Have we implemented an add already? No. Okay. Anyway, alright. Where is compare again? Let me just go back and check out compare bit instructions. Right, this is compare. So we haven't done any of the other like compare to X types or anything. We'll have to come back and do them. Anyway, alright, so we want to, let's just do it then. So we've got an ADC. So we want to add the value equals CPU.areg plus add with carry. ADC results are dependent on the setting of the decimal flag. In decimal mode, addition is carried out on the assumption that the values involved packed in BCD. There is no way to add without carry. Okay. Yep, so let's just copy this definition. So it's the areg plus the value that comes from memory plus the carry. And we want to store that in the areg, cpu.areg equals add a value. And we want to set the carry bit defined on whatever's in the areg, which sounds around right. Now, the only question is, how do we get this carry bit? And that I'm not quite sure. Add memory to accumulator with carry. So where do we get the carry from? I mean, we'll know based on the flag on whether the last operation had a carry. But yeah, this is going to be interesting. I'm not quite sure where we're going to get the carry from. Carry. Well, let's look for the carry and let's see what happens. So we're probably going to have to check if the decimal bit is on as well. I'm unsure what we've got to do here. So let's just try implementing it without the carry. Let's see what to do. Carry. Let's see if this works for now. So it does. Add C. No, it does not. Instruction not found 6.9. Right, because we haven't implemented all the different ADC modes. Alright, so let's chuck them in. Let's just copy this across. ADC, ADC, Yep, and then cool. So now when we do this, instruction not expected, and this is because our carry bit is different. So now let's check the NES test log and see what we expect. So here's our ADC, and it's with the value of 69 in binary. Sorry, in hex. So we're adding hex 69 to whatever's in the A reg, which is 0. And so the answer is 69, which is kind of what we expected. So let's see why we think it disagrees. It's probably the carry flag or something. P-match, perhaps unsurprisingly. So what's different, again, about these? So just by looking at it, it looks like the highest byte is set in this one, whereas not in the other one. 0011, 0. Yep. 11, whereas the expected P 1. So 0, 1, 2, 3, 4, 5, 6. The 6th byte is set when it shouldn't be. So 0, 1, 2, 3, 4, 5, 6. So the V, the overflow, is set and it shouldn't be. So 1 if last ADC, hey, this is what we're doing, or SBC resulted in signed overflow, or D6 from last bit. So how are we set? So what we're saying is the expected thing is that it did not overflow, which is true. Overflow bit, right. So we've just coded the overflow bit to be D6 from the last value, which it really shouldn't be. It should instead be 1 if the last ADC or SBC resulted in signed overflow. Right, so we want to do a conditional kind of thing here. So when we're doing a bit C package, we do want to be doing a comparison. Yeah, okay. So let's have two things here, which is sets overflow bit. And let's say the current one we've done is sets overflow bit explicitly, which is going to be based on, so from the value. And then we also want to have sets an overflow bit from arithmetic. And then actually ADC, we want it to set it from arithmetic, and then in our status, if instruction dot sets it from arithmetic, then we want to do a set if the carry is set. Where 1 if last addition or shift resulted in a carry. So how do we know it resulted in a carry? So it resulted in a carry if value is greater than or equal to FF. Something like this. Now, the carry will actually mean that it will never be greater than this, and that our add C should take care of this. So really, instead of setting the overflow bit from value, instead of doing this actually, probably what we want to do is manually set it in ADC. So let's go back to here. So the add C thing should CPU dot status reg dot bits status types dot overflow, and that should be if overflowed. And overflowed is just going to be true if, so if add a value is greater than or equal to, no, it's greater than 0xff. So if it's greater than a single byte, then we want to say overflow equals true. Oh wait, is overflow different to carry? Oh shit. No, I'm getting confused. Shit, okay, so the overflow bit was the one that was wrong. Okay. Overflow, if the last ADC resulted in signed overflow. Okay, yeah. So let's say overflow equals false. If it's greater than that, then added value equals added value mod by 0xff. I mean, if you mod by 10, it should still equal 1, right? So if we get 256, this will make it equal 1, which we actually want it to equal 0, right? Let's see. So A equals 255. A mod 255 equals 0. So what is 256 mod 255? Yes, we actually want to mod it by 256. Which is 0x100, right? So overflow equals true. And we want to set the overflow reg on whether or not it overflowed. Cool. Let's try that again. ADC immediate. Right, so what's different now? 100, 1101. They look the same to me. Valid. A match. So now our A doesn't match. Alright. Hey, good morning, Danny. Have I missed all the good stuff again? Potentially. So kind of what I've been working on today is more instructions. Particularly what I've implemented is basically something where you can just paste in, so from this eTradition site, you can just paste this in and it'll automatically generate all the classes for you based on the data that's in this. So it just generates the classes. So it literally comes in and builds them by matching the string to an addressing type, and then you pass in like whether it's an or an and it basically just pulls the addressing type out and the what are these called? The identifier bits. And so it sets the identifier bits, sets the addressing type for you. And so all you need to do to implement like 6 types of different EOR address, instructions now is you just implement exclusive OR. So you just say areg done with the value, and then you come back and you just paste this in, call this helper function, and it does it all for you. Sweet, indeed. So I'm kind of just trying to cut down on some of the like typing that I have to do. And so this is kind of why I wanted to do the what do you call them? Yeah, mix-ins and stuff like this, because now it's quite easy to construct these things automatically. So just by like parsing a string and using Python to do dodgy stuff to create these classes and remember them and stuff. So now it all happens auto-magically, and I don't have to do any typing beyond copying and pasting this this thing and defining the base class. Which is pretty cool, which is where I kind of wanted to get into for a while, but it was always around the corner. Let's see, what was going wrong here? Right, so our A is wrong. So what's our expected A and what's our actual A? Makes sense, the copy pasting could get a tedious. Yeah, exactly. So I kind of got sick of doing that, and so I just have something that can pass it all for me now. Oh. And also, it's going to reduce the amount of errors that I have from, copying, pasting, and writing out addressing types and stuff. CPU.areg is 1 off. That's funny. So what's my added value? So it should equal 107, but you're telling me it equals 106. And right here it equals 105. 106. Alright, so I do 2. The first one is 105. And then the second one, value, added value. Right, so probably needs the carry bit. Okay, so let's presume that we just add 1 for the carry bit. I have no idea if this is true. Is the carry bit set to true? It is set to true. Also, we should probably set this to an int. Right. Cool, so now we're at another add C. Is that right, Danny? Is the ADC, you add the thing from memory, you add whatever's in the accumulator, and then you add, I'm just adding 0 or 1 depending on whether or not the carry bit is set. It's kind of what I think it is, but I'm just, pretty much making that up. Alright, so what doesn't match up here? So P doesn't match. 0, 0, 1, 0, 0, 1. Oh my god. 0, 1, 2, 3, 4, 5, 6. So the 6th bit. The 6th bit is wrong. So where's my status? I think that's right. Yeah, cool. Okay. Yeah, I don't even remember where I've implemented the carry bit stuff. I'm kind of relying on NES to pick up if I'm going wrong. Alright. So sets the carry bit. Yeah, I just do if it's less than 0. I set the carry bit. Huh. Oh, right. Okay. So if it's 2's complemented. Wait, what? Okay. No, I have no idea. I don't know why I did this. Oh, jeez. Yeah, I add on carry, but also set carry in ADC. Do I set the carry in the ADC? I set the overflow in the ADC. Let's say var result equals accumulator plus value plus carry 1 or 0. Yep. Then carry equals the results and 256. Right, okay. So if it's over 256, you set the carry. If both inputs have an opposite sign to the result, it's an overflow. Right, so I just set the overflow by literally overflowing it in a byte range. Who knows? Who knows whether that's right at all, but carry equals that. So why would I set the carry on it being less than 0? Is that something I've done today? This is one of those questions that I should be able to figure out. Alright, where's my NES repo? So, status. Yeah, I did add the sets the carry bit to be bool is less than or equal to 0. So why would I have done that? And that probably comes from somewhere in here. Or in here. Yeah, so this is why I did it. Right. So when I was comparing, compare sets flags of subtraction have been carried out. If the value in the accumulator is equal or greater than the compared value, the carry will be set. Yeah, so if it's a negative for a compared, the carry will be set. So probably the status reg itself shouldn't actually set on whether the value is less than 0. Oh, I don't know, maybe it should. But that's definitely what you need to do for compares, but we'll see if anything else sets the carry bit, which I'm sure it will. I mean, ADC I know is going to set the carry bit, right? Sets the carry bit, but we want the ADC also is going to set the carry bit, right? Yeah, it does set the carry bit. Yeah, so we actually want compare to separately set to do this. So we want compare, so sub equals that, and then we want to set status reg, the carry bit, to be of whether sub is less than 0, and then return sub. And then I think we just want this status thing to, instead of being this, is to be ANDed with 256. All I remember is this was all really confusing, and every time I fixed it in one place it broke. yeah. Sounds around right. Alright, well, let's presume that this is more right. I think find usages. Where do we set it? So we do want the ADC to set it, but we don't actually want compare to set it. We actually just want to do in compare. We'll do it locally, just if the sub is less than or equal to 0. Okay, so where are we up to? Yep, so I think it's still wrong, but that's fine. So what's different here is the 6th bit, which was indeed the overflow bit. Is different. 0, 1, 2, 3, 4, 5, 6. Yeah. So the overflow bit, 1 if the last ADC or SBC resulted in signed overflow. So we expect it to be 1, but it wasn't set to 1. So where's my ADC? So how many overflows in am I? ADCs, man. 1, 2, 3. Yep. 1, 2, 3. Right, so what's my added value now? 255. So if added value is greater than or equal to 255. So it's saying that that this is an overflow. Overflow 1 if the last ADC or SBC resulted in signed overflow, or D6 from last bit. I mean, the binary of 0xFF is not... Oh, shit. So we can only go up to negative 128. Oh, crap. Okay, that's where I've gone wrong. Right, because it's signed. Yeah, that makes a lot of sense. So EF, right? No, not EF. Great question. What a blood clip. I don't know. I could answer that better if I lived in America, I suppose. What the hell? Am I going crazy here? What is 127 in hex? 7F. Right. Okay, cool. So if it's greater than 127, then we want to mod it with 80. No, we just want to say it has overflow. So overflow is true. Sets the negative bit. Sets the carry bit. So we're setting the overflow bit here. The carry bit. Carry bit is going to be set if the topmost bit is set. Jacket, is it cold there? It is cold. I'm in the middle of winter. So I also have some very nice gloves on because it is pretty cold. But hello, Shelly. Schmelly Orc. Schmelly Orc, that makes sense, I suppose. Alright, let's... Yeah, alright, fuck it. Let's just keep going. See what happens. Carry is based on the topmost bit. Overflow is based on if the sign changes. Yeah, winter, Aussie land. What? Winter can be cold, I suppose, in Australia. What is the temperature at the moment? 10 degrees. That's pretty cold. It's pretty cold for me. Alright. Cool, so we're still in this add C, and the answer is, which I discovered before, is that the overflow bit is not being set. Right, okay, so I'm going to figure this out. So that's overflow from values, so we're manually setting the overflow bit. So the third one is the one that we care about. And added value is 255 if added value is greater than this, which it is. I guess Aussie land is in the future. Presumably in a different hemisphere as well, to America or wherever you're coming from. Which flips the seasons, funnily enough. So we're in the height of summer at Christmas time. If added value, cool. So why is this breaking? Because the overflow bit is set and we expect it to not be set. It did result in signed overflow? No, so it's saying that it didn't result in signed overflow. We expect it to not have resulted in signed overflow. Okay. Came from the Reddit thread following your channel now. Just want to say I'm enjoying the stream. Thanks, Lacozy. I appreciate that. Lacozy? Lacozy. L.A. Cozy, I suppose. I'm one of those dirty Canadians. Fair enough. Very dirty. I lived in Canada for a while. Get mega hot in the summer. Last year was 101F. Yeah, so I lived in Canada for one winter. And that was like proper cold. So, you know, here seems pretty nice now, but still it was, you know, you get used to wherever you're living, so. Cool, so I'm going crazy because I have no idea what I'm doing wrong, but my guess is that this was right in the initial thing, but I shouldn't be modding it. So let's see if that fixes it. Nope, we're still, so we're not setting it, but now we do expect it to have overflown. So the self-expected A is 255, and the A reg is 255. We're at C951. So if those things are true, we expect the overflow thing to be set. Yeah, this stuff looks complicated. Yeah, it's not in a great place at the moment. I do networking game development. Cool. Developing a network game, is that what that means? Network, or like networking people that do game development. Right, alright, so let's look up ADC. Do I ever do a set decimal? Oh shit, I do. Okay, so it actually does depend on what the decimal mode is. Ah, crap. Alright, the decimal flag controls on how it adds and subtracts. If set, arithmetic is carried out in packed binary coded decimal, so in BCD form. The implication is that it should be included somehow. Right, and if it's in ADC form, which is what I think it is, if it's in BCD form, assumption is carried out on the assumption that, okay. So, let's look here. When we come down through ADC, are we ever in, holy shit, are we ever in BCD mode? So, CPU, oh, the decimal flag does nothing? Well, that looks nice. Game development of client server, front end, back end, cool. 512 slash protections. Sounds very impressive. Sorry, NES. Okay, so I'm going to ignore that. Do you have any idea what I'm doing wrong here, Danny? That is a link, decimal flag. Because it does appear 6502 supports decimal, but in NES it doesn't do anything. Yeah, okay. That's sweet. Because here I'm expecting the overflow flag to be set, but it's not. C951. And if I go back to here and I change it to 7F, now I expect it to not be set, and it is. Right, okay. This is, yeah, this is what you're talking about, where it's like, need to flip it sometimes. Overflow, bitwise order with results, ended with, holy shit. If both inputs have the opposite sign to the result, it's an overflow. Ah, right. So, cool. That makes a lot of sense. Yeah, so in my ADC thing, I should be doing overflow is going to be, so if both things have separate signs to the result, it's an overflow. Can't find it, but yeah, that's alright. This is all, that's life. Alright, so if the added value Oh, right, so you do the accumulator. Yeah, okay. Have, the result set overflow. So let's call this result. Let's cut that out. CPU set to the result. Okay, so we're gonna make this a bool, and then it's gonna be CPU.areg, and you're saying bitwise or? Don't see a lot of 3DS emulators. All I see is a fake one. Why hasn't anyone made any of those yet? I don't know. I guess the basic principle is anything newer is a lot harder to do, both from like a technical perspective, and I think also the more recent you go, there's a lot more like copy protection and stuff. So my guess would be it's a lot easier to do things that aren't newer, and the 3DS is still kind of relatively new. Copy. Right, so carry indicates unsigned overflow, overflow indicates signed overflow. You beauty. That is nice. Okay, so let's just copy that. Overflow is going to be the bool of CPU.areg result value result mod bitwise ended with 80. Cool. You know, one of those things. All right, let's see. Shit, that didn't work. All right. Oh no, it did. We're setting the another flag wrong. Setting the p match, and we're setting the second thing wrong, which is Z0. And the reason for that is because the CPU.areg equals 256, and our expected 0 is 0, because we should have actually overflowed. Or carried. Maybe carried is the better term. Yeah. So if carry bit yeah, okay. So let's do if greater than 255 carry. So if it's greater than 255, result modded with 256, and we want to set the carry bit to be true. Otherwise, we probably want to set it to be false. False. Yeah. Now, is there any reason, Sophie? Yeah, we just want to flag this kind of stuff. So there's no real way to tell from in here instruction value. So by this point, the value's already been cut down to something. Yeah, it's already been looped around, so it's already been carried. So let's just get that out of there. So it's the carry bit, whatever. Cool. So we'll just have to set the carry bit manually. Another exception. That's perhaps unsurprising. It looks like the last bit, the least significant digit, is incorrect. Alright. The carry bit is incorrect. Yep, that's unsurprising. So the expected A is 255. Ah, shit, this should be greater than 255. Make it greater than 256. Okay, so we made it further this time. Hey, we passed ADCs. Alright, we're back onto compares. Right, so what's different here? 101, 001, 01. So that looks like the most significant bit. The most significant bit is the negative bit, set to bit 7 of the last operation. So we've done a compare, and we think that it was negative. Negative if set to bit 7. So my bit was set and their bit was not set. Interesting. Set to bit 7 of the last operation. Alright, well, let's find compare. Let's go. 2, 3, 4, 5, 6, 7, 8, 12. Man, we go through a lot of compares. Alright, how can I find this? So it's where compare is true. Oh wait, this is setting the negative bit automatically. So how's the negative bit set automatically? So it's not bool of value. No, it's 0 bit, sorry. Negative bit is bitwise AND it with this. Okay, and we return the value. Let's just print sub. Right, so the value is -1. And then here what we expect is that it's not negative, whereas we're saying it is negative. I agree with our assessment of the situation. Alright, so let's put a breakpoint here if sub is less than 0. Yeah. This is where we expect to be. So the value is going to be 63 and the CPU.areg is 64. Yeah, which makes it negative. So let's go back to sub and let's see, was it called sub? No, it wasn't, it was compare. Compare sets flags as if the subtraction had been carried out. If the value in the accumulator, you're doing value minus A. Yeah, it should be A minus value? Probably. If the value in the accumulator is greater than or equal to the compared value, the carry will be set. The equal signs will be set based on the equality or lack thereof, and the sign of the accumulator. Alright, well, it's a pretty easy way to find out, hey? Yeah, so I think that makes it wrong as well. So now my least significant bit is set, not set, not set, and it should be set. So the carry bit should be set. The carry bit should be set. Yeah, so the carry, right, so value minus CPU.areg, but then the other one should be set on this. Carry and with 256 equals 0, and then set Z based on the byte of the result. Yeah. Byte of the result. Right, so what you're saying is if I go to here, what is sub equal to? Yeah, don't know. Sub and with 256 is not going to be true. Let's see if this works. I think this works. Yeah, that worked. Yeah, okay, so the carry bit is set on value minus areg being less than or equal to 0, which is the same as saying accumulator minus value carry is set on accumulator on result being ANDed with 256. So I'm pretty sure if I go to here, if I copy this, that's weird. Accumulator minus value, which equals 0, and then result that equals to, oh right, that equaling 0. Yeah, so these are going to be the same thing now, but your way makes way more sense. And it's just sub mod 256, and I think it's going to be not the bool of this, right? Yeah. Cool. Yeah, I think A minus value, which is my sign extended 8 bits of, yeah. Nah, I think this works. I was just writing it. Yeah, I was doing it the wrong way, but it just happened to work for half of it, but not for the other half. Alright, instruction not found C0. That's always good. New instructions. It's been a while since I've done one of them. C0, copy. Or compare Y, more likely. Compare memory and index Y. Right. So we've got a compare function, but this is actually CMP. So really what I want is to write a actual compare. With a given register. Actually, maybe that doesn't make sense. I'm going to have to shoot in work early on my birthday. Wait, is today your birthday? Happy birthday, if so. That's awesome. I'll catch up what you made. Hope to see you finish all the instructions. I don't know if I'll make them through them today, but I will at some point in my life. Thanks for coming along. You've been really helpful, as always. I think I struggle when I don't have someone who knows what they're doing around. So, yeah, thanks for coming along. Happy birthday. Cool. So the only thing we need to change is CPU.areg. Yeah, so let's just get the value. So super.write. Yeah, I know that feeling. Yeah, I think we'll have to collaborate a bit more once we're both on the PPU. Thanks, Danny. Enjoy work. Hopefully. So CMP is just going to return CPU.areg minus value. Whoa. So, sorry, in this one we want to call super with these things. But instead, I want to return, so result equals cpu.areg minus value. So I want to pass in result. And now the value that it gets in will actually have already had the stuff done to it. We'll already have had the areg minused. Right, so now we can do a compare with the areg. We can do compare, we can do cpx, and we can do cpy. cpx and cpy with the yreg. And all this function does now at its core is set the carry register, which is just something that's kind of useful today. Alright, so cpx, let's implement all of them. So where's my CMP? It's up here. So let's add cpy. And cpy. So we've now got cpy instructions, and we can add our cpx, so compare to the x register. And all we actually need to do now is cpx, we need to copy across the correct types of addressing. And cpy, we need to copy across the correct types of addressing. Boom, alright. How far in are we? Not that far. Compare results not expected. Oops, okay, so I've broken this somehow. And that's because these should all inherit from compare, not from instructions. Boom, so now how many instructions in am I? Jesus, a lot. Instruction not found, E9. Alright, more instructions. We're back to implementing more instructions. E9, SBC. Let's find out what SBC stands for. Ah, subtract with carry. I suppose that makes perfect sense. Effects flags, all of these flags. So this is probably going to be pretty similar to our add thing, but we're going to have to implement it slightly differently. So SBC results are dependent on setting the decimal flag. Yeah, whatever, we don't care about that. There is no way to subtract without carry, which works as an inverse borrow. Holy shit. If a carry is cleared by the operation, it indicates a borrow occurred. What? Yeah, I have no idea what that's trying to say. Alright, let's let's make a class that does that. So where's that? Add ADC. So it's going to be very similar to this, except it's going to be subtract with carry. Right. SBC. So let's copy this definition. Doesn't set the carry bit. Does set the carry bit. So it sets the negative, sets the 0, sets the carry, sets the overflow. So similarly to add, we're probably going to use these automatic negative and 0 setters. but we're going to set C and V manually ourselves. Alright, minus and minus. If value and areg have different signs to the result, set overflow. Sure. If it's greater than 255, this is probably going to be if it's less than 0, invert. So I would say if it's less than 0, result, add 256. Yeah, we don't need to set the carry flag though, I don't think. Maybe? Do we? Do we need to set the carry flag? It says the carry flag. Let's presume that it does. Alright. Yeah, that looks around right. Let's give that a shot, see what happens. Instruction not found. Fair enough. That does make sense. Because I haven't implemented them. So SBC. SBC types. And what are my types of SBCs? Oops, wrong browser. All of these. Done. Alright. Instruction results not expected. Yep, so SBC is not implemented correctly. Which makes sense. P match is the only thing that's wrong. No, A as well. Okay. So we expected A and we expected 0 and we got 255. So let's look at it actually in here. Let's see what happens. So what's our result? -1. Because we expected A to be 0 and in fact it was 255 because we overflowed. Right, so what values are we actually doing? So what's CPU.areg? 64. What's our value? 64. And what's our carry? Is 1. So I think either we do want this carry, but it's probably going to be not this. So now result should equal 0. Yep. SBC immediate. Oops, I cleared all my watches. Alright, so what doesn't match? P. Perhaps unexpectedly. So what's our expected P and what's our 2 in? 38 versus 39, which means that this one has the least significant bit set and this one does not have the least significant bit set. So why wouldn't it have the least significant bit set? Alright, which is what? The carry bit. So our thing does not have the carry bit set when it should have the carry bit set. Carry 1 if the last addition or shift resulted in a carry, or if the last subtraction resulted in no borrow. Cool. So let's go. Let's presume that this is the first SBC 2. No, it isn't. This is ads. Where's my subs? Yep, okay. So we actually want the carry bit to be set based on whether the last subtraction resulted in no borrow. So is the result less than 0? No. So we want the carry bit to be false. So probably we want this carry bit to be true. It only carries if we don't, if we don't do an inverse carry, whatever you want to call it. Yeah, so that works. So if the result is less than 0, we wrap it around and we say it wasn't a carry, even though, because it's inverted because it's subtract. What's the term? No borrowing. Whereas this one did result in borrowing if you just a normal, I guess. Alright, instruction not found, C8. C8, see you later, mate. C8. INY. What the hell is INY? Increment index Y by 1. Register instructions. Okay. These instructions that are of implied mode have a length of 1 byte and require 2 machine cycles. What? Okay. More. So let's just implement these. All of these. So these can go in bit instructions. That's where I want to put them. Okay. Register instructions. So we got tax. Let's just chuck these in a comment down the bottom and then we'll work off them. So class tax, and these are all going to use implicit addressing. And they're all going to do some crap, whatever. So let's say it inherits from instruction. Transfer A to X. Well, let's do I and Y to start with. Increment Y. Which is just going to be implied. It's going to set these things. The negative bit and the 0 bit. Yep. The identifier bytes for I and Y is going to be C8. And then the write function def write. So what do we want to do for this? We want to increment the Y index Y. I'm assuming that's the Y register. Right, so CPU.yreg plus equals 1. Cool. Now, I presume these are all going to do the same thing. So they're all register instructions. Good morning, Everex, and good morning, Kex123511. Good afternoon. It is afternoon. Here, at least. But, good morning or good afternoon. Alright, so I and Y. So let's create something in these base instructions that's going to be a register instruction. It's going to set registers. Register changer modifier or something. Because we know what these are going to do. And they're always going to do these things. They're always going to set the negative 915 time. They're always going to set negative in the 0 bit. Cool. So here, this should in from register modifier. And then we can get rid of all this crap. A NES emulator! Exclamation mark. Is it morning because you're British or Aussie? Aussie. Close. Okay. Well, correct. If I was in Britain, it would be something like 4 and 6 in the morning. Maybe. What time would it be in Britain? 6 AM in the morning. No, it's around 4 PM here. I'm playing around, let's say, learning Rust. Awesome. So I presume, so what I kind of why I started doing this was the guy, what's it called, Ferris, who was creating a Nintendo 64 ROM in Rust. So I presume yeah, you've checked that out. And if you haven't, you should check that out because he's kind of doing what I'm doing, except doing it in Rust and with a bit more of a modern console. So that's really awesome. But that's too crazy for me. Yeah, that's true. I looked up GMT time, but GMT time is not actually British time. Cool. So we have I and Y, which is just gonna do this. Cool. So let's have a decrement Y day, which is going to be 88. It's going to minus the reg, then decrement X, decrement Y, so in X, in excess, dex, so dex is going to be CA, and I and X is going to be E8. And these are both going to change the X reg as opposed to the Y reg. Cool, okay, so I'll come back and implement these other ones then. Where are you in Europe then? Spain, France? Well, if it's 8 here, it must be pretty close. So, presumably France. Maybe one of the Eastern Nordic countries? Oh, Keck, sorry. I read that the wrong way around. Yeah, you should check out Ferris streaming the Rust emulator. Alright, unsupported types. That is unsurprising. So let's go into our, which one is it? I and Y. Right, so we've got to return the value. Okay. CPU X plus equals 1, and then we want to return CPU.yreg. Return the yreg. Return the xreg. Return the xreg. Cool, alright. No, keep going. How many instructions are we down? I'm too noob with Rust at the moment. Yeah, fair enough. I haven't really tried out Rust. It seems pretty cool. Just after watching that. But, kind of... Yeah, I've kind of mainly done Python and C++ stuff, so it seems interesting coming from maybe replacing C++ with it, but... It looks... Yeah, like I'd need to sink some proper time into it before I could really get into it. Back again. Hello, Black Stealths. Welcome back. We are still going. Onwards, ever onwards. Alright. Let's see actually how many instructions we've implemented now. 117. We started today at roughly 60, so I've kind of pretty much doubled the amount of instructions we've implemented. Which is pretty good. We're maybe, I think there's 150 instructions. Something like that. So most of the way there. Or maybe with unofficial instructions, maybe it's 255. So we're somewhere between half and 2/3 of the way there. In terms of instructions, but we've definitely sped up a large amount, so it should probably only take one more session or something. But that's just obviously the CPU. That's not anything else. Yeah, last time I was there, we were at 62. Yeah, so I've kind of been smashing through them today. The way I've been able to do that is kind of the new hang on a second, let me just get this. Yeah, so this where we can now generate the instructions just based off pasting in the kind of documentation notes. It'll parse this, get the type of addressing, and add it to the base class, and then all of these instructions will be defined. It seems freezing cold over there, coding with gloves on. Fingerless gloves, so it can't be too cold, but no. It's around 10 degrees at the moment. I looked it up. Which for me is cold. Probably not if you live in Europe, though. What's going on here? So, which instruction are we looking at? SBC. And the value for the sreg is wrong. That's a classic. 001. Yep. Okay, so our 6th bit is unset. So the second highest bit. V, overflow. If the last ADC or SBC resulted in signed overflow, or D6 from the last bit. Alright. So let's look at our base instructions. So our add, which one was it? Overflow. So if value and areg have different signs in the result, set overflow. And here, if value and reg have different signs, set the overflow. So here, the overflow is central heading. Yeah, no, don't have that. Yeah, I think if I spend my time coding NES emulators on Twitch, the central heading is a pipe dream. One day maybe. So let's presume that I've done something wrong here. So the areg and the result, the value and the result. Cool. So Danny posted a link a while back about how this was done. Here's the page. I think I found it from. So let's look at this. So this is for ADC, but for SBC. Yeah, I wonder if they have anything. For how the code works, positive plus positive equals negative, and negative plus negative equals positive. Alright, so let's find SBC. The clearest way to set is to test if the result is major more than 0xff. Yep, so if the result is greater than 127, set the flag. Okay, that seems really good. Uh, 127. Let's find that out. Hey, CJ4 Beatboxer. What is going on? Oh, have I broken it? I've broken it. Alright, let's look at the areg. So 127, and we're saying that the overflow, so the overflow should be set, and we're saying that it's not set. Wait a minute, 1010011. Yeah, so it's the 2, 3, 4, 5, 6. It's the 6th bit, yeah, which is overflow. So, at 127, it should be set. Should be set. Is that what this thing guy says? Nope, he's saying greater than 127. Base instructions. Let's check if this works up here. Result greater than 127. Does this break my adds? Yeah, it does. Okay, that doesn't work. So let's put this in here. Let's chuck a not on this. Let's see if that works for now. Story of my life. Alright. 1110011. Yeah, okay, so this is the 6-bit again. And this is when the areg is equal to 0. Right, so clearly something is going on. So we want the overflow to be if the areg result and then the value and the result are ANDed with 80. I believe there's 2. Then use int bool a with m and 0. Both algorithms throw different results. Yeah, okay. So they do throw the same results, they're just, this guy screwed up. So this is the one that I have implemented, which is 2 ANDs and 2 bitwise ORs with the ADC. Yep, so the ADC, areg, bitwise OR with the ADC, and then the value from memory bitwise ORs with the ADC. Then ANDed that with 80. We want the bool of that. Holy crap, okay, so NES, SBC, overflow. I struggle trying to find documentation for the Dreamcast CPU SH4. Yeah, that doesn't surprise me overly. I haven't looked into any of the Dreamcast stuff, but any kind of old emulator stuff is a bit hard to find information on unless it's quite commonly emulated. Like the NES has quite a lot of information, but if you went back and tried to find a Sega Genesis or even Dreamcast, yeah, 6502. ADC. Welcome to the arcane halls of the 6502 add and subtract. Pretty much the toughest 6502 instructions to emulate. Okay. SBC is easy to implement once your emulator has ADC. All you need to do is invert the bits of this argument, and pass that to the ADC. Oh. ADC, invert the bits of the argument. Whoa. Two positive numbers and added results in negative, two negative numbers. Two numbers that have the same sign are added, and the result has a different sign. The overflow flag is set. A with the arg, A with the sum. Yeah, holy shit. Just kill me. Kill me now. So the decimal equals 1, which it doesn't, because we can't have decimal, thankfully. So the overflow is going to be equal to areg bitwise doors with the result, ANDed with the memory, bitwise doors with the result, ANDed with 80, equals 80. If it equals 80, then 1, otherwise 0. That equals 80. So that, this whole line is now going to be false. SBC. So now we expect it to be, now we expect it to be 0 and it's 1. What does the ADC command do? So the ADC is add with carry and SBC is subtract with carry. So basically ADC is just take a value from memory and add it to whatever's in the A register. And if there's the carry bit is set, add 1 to the value. Whereas SBC is kind of like the inverse of that, right? So take whatever's in the areg and then minus the value from memory and minus the carry flag. And it turns out that they are quite hassly to do with how they set in the overflow bit and stuff like this. Because over here, for instance, we expect it to not be set, and we expect, but we have set it when the CPU reg is equal, areg is equal to 255. So how many? So 1, 2, 3. Yep, so 1, 2. Why is it so hard then, or is it hard to do fast? No, it's just hard to do in general. The logic for why you set the overflow flag versus the carry flag and stuff like that seems to be like crazy. It's not as simple as like doing an overflow check. So here we have to check, for some reason I have no idea why, but if the value in the A register have different signs than the result, set the overflow. So basically, if you have a positive and then your result is a negative, then you've overflowed. And obviously the same with the other way around. So if you've got a negative and you set that. So yeah, it's a little bit confusing. I'm not fully understanding it, but from what it seems like from that answer on Stack Overflow, this is a problem that people commonly run into. So here we have 2 negatives. So what's cp.areg? Yep. What's value? And is this is 0? Yeah, okay. So we start at 64, we minus 65. I think that'll be the same case if you're doing math in C with the carbide tab. Yeah. Carbide tabs would probably make my life a bit easier. I could probably code my own in, but doesn't Python do it all within so much? Yeah, everything's an int. Oh, whatever. Everything's a Python number. So there's no implicit overflow or anything. So I'm manually putting all this stuff in. Which is kind of, you can see down here, I'm doing, which is why some of this is all a bit harder, because I'm manually managing my tabs. I should probably just write a custom wrapper for a byte class, honestly. But for now, I will power through, because it looks like this is difficult regardless of whether or not you have overflow, right? So basically what we're saying, if value and areg have different signs than the result, what is the result? So these all have the same sign. No? CPU. Yeah, they both have different signs to the result, then set the overflow. overflow is true. But we expect overflow to be false. Right, okay, so clearly I think it'd be easier in Python if you simplify it. Yeah, potentially. I didn't see this link earlier. Danny posted a link to his code where he does it. So his ADC is going to be accumulator with the result ANDed with the value of the result, ANDed with 128 does not equal 0. Yep. And then where's his SPC? Yeah, so he's just done with SPC. It's the same as ADC, but with bits inverted. Holy shit, yeah. Alright, let's see if this works. So let's make an inherit from ADC. And then just pass it in. So CPU, memory address, and value with the bits inverted. Nope. Alright, cpu.areg, self.expected-a. 1111111. Alright, so the second least significant bit, oh jeez, just going to be 0 bit. Should be set to 1. I agree, it should be set to 1. And casting it to a byte. So what does value equal here? So what's the inverse of value? 191. Yeah, okay. So what's the result? 256. It's 191 plus 64. So is the overflow? No. And does it equal 0? It should equal 0. Result equals 0 now. Yeah, and the carry bit is true. cpu.areg equals result, return cpu.areg. cpu.areg now equals 0. And therefore, the 1 result the 0 bit should be equal to 1. Alright, so does this not set the 0 bit? It does set the 0 bit. So let's go. So STC, oh shit, we're gonna return it. That's why. Yeah, that worked. Dang, okay. So due to some weird properties of things, we can just invert the bits and pass them through to the ADC. Nice. That's way easier than trying to figure shit out. Alright. What am I broken on? I and Y. And why am I broken? The P's don't match. And that looks like the 0 bit doesn't match for I and Y. So let's find our I and Y. So what does the CPU.yreg equal? Now that we've updated it, 114. Right, CPU.yreg. 115, 16, 17, 256. Right, so we'll just need to implement a wrapper around this in register modifier, where we just make sure that it doesn't, if it wraps around, you know, we basically ensure. Have you ever tried PyPy? No, I haven't. I kind of know it exists, but to be honest, I haven't used it. Speed, memory, compatibility. Cool. Thankfully, we're not at the point where speed is going to be an issue. I wonder if I have byte. Yeah. Int byte. No, not that. Its main plus is that it's faster. Yeah. The reality is this stuff, hopefully because it's a NES, will be fast enough. But yeah, I could just plug it into PyPy. Yeah, for when I do want speed. Yeah. No, this isn't what I want. So really what I want to be doing is kind of, instead of this shit, really what I want to be doing, right, is CPU.yreg. And then when I say yreg is here, kind of what I want to do is, instead of making this equal to 0, I want to make these byte types or something. What I could do as well is at property def xreg return self.xreg. I could do something like this, right? So now when I find xreg, return self.xreg, yeah, fuck that. I was going to do like getters and setters for that, but Python override int, or inherit from int. Yeah, so I kind of want them to be a byte. Inheriting built-in types is very seldom worthwhile. It's almost better to use composition. Instead of inheriting string, you would keep a string object as an attribute. Yeah. Because I don't really want to be doing this where am I? Here. So I want to kind of do, if I add one to the CPU.yreg, I kind of want it to automatically overflow. Yeah. How about using byte array? Yeah, byte array is an interesting one, because it's, yeah, bytes are really weird. They're not like bytes in C. It's like a bytes array. If you do like this, this is how you declare a bytes array. And then to get the first byte, it's like literally a, you know what I'm saying? It's just a list of bytes. And you can't have a single byte, you've got to have a list of one byte. A list of bytes that is one long is the only way to store a single byte, if that makes sense. Which kind of sucks. Yeah, that's my assessment of the situation. Yeah, okay, so let's, screw it. So if it's greater than or equal to 256, mod equal 256. 256. Let's find out where I use this. Yep. Into byte. Yep. So I kind of want the result to be a byte of that. Let's do it. Fuck it. Byte. So if value is greater than 256, self.value equals value mod 256, and if value is less than 0, self.value self.value mod equals 256, and if it's less than 0, we'll just add 256. Yeah, I think that makes sense. And we'll say by default it isn't wrapped, but if it does either one of these things, it has wrapped. And then how do we define a plus operator? Python addition operator. 255, yeah, because I want it to be, yeah, you're right, greater than 255. I'll make it greater than or equal to 256. Fine, greater than 255. Mod 256 and add 256. Alright. Python override operator. Init string add. Is this going to be add? Yeah, okay, so self.value equals self.value plus other. Self.normalize. I'll just define my self.normalize function. Normalize function to do this kind of shit. So if self.value is greater than 255, right, so now if it's greater than 255, yeah, if it's greater than 255, then it's wrapped. If it's less than 0, it's wrapped, otherwise it's not wrapped. Cool, so def sub, presumably. Is there like a set or something? No, how do we... Adding, comparing, don't really care about comparing. I don't think so, because if you're greater than 255, so say you're at 256, we want that to, because, how do I put this? If you're 255, that's a valid value. If you're 256, we want to wrap that around to 0. So you've got a minus 256. Similarly, if you're at -1, then you've got to add 256 to get to 255, which is the maximum value. So I think it's your maximum value plus 1 is what you need to, like this is what I'm trying to say. I think that makes sense. Alright, so where am I in my CPU? So where's my Y register? So my Y register is going to be a byte. 0. Now I kind of do want it to inherit from You can't really override equal for assignment. Yeah, fair enough. So I kind of do want this to inherit from int, I think. Yeah, set method. I think I want this. This is what I want. Five. I just want this to be like arg0. And then basically, if I add, I just want to do a super other. And then normalize. Normalize. Value. No, can't do that. So we'll probably need to return a new object, which we'll want to normalize. Interesting. Yeah, this is going to be a pain because we can't modify anything, because int is immutable. Actually, I think what we want to go back, but we want our get thing. So I think we can overwrite the get attribute, get item. That'll be a ton of created objects. That's right, I only want to do this for the regs though. So I think if I do get return 1. So what happens if I do this? And I say that this is going to be a byte. Oh, sorry. So now if I do self.yreg, it's a byte. How do I do like the default Python override get? Can I override like by default what it returns? Since now reg plus 1 won't return a new value. Yeah. Yeah, alright. Let's kill this idea for now, until I can think about it a bit further. Where we at though? So this code, let's just copy this. We can come back and figure this out later. So if it's less than 0, add. Put this down to here. We'll put this down to here. Probably the easy way of doing this is going to be creating accesses on the CPU registers. Would be more proper to add methods on that byte, like add sub. You're right. But for now, because I kind of want to be able to access it as an int, is my thought. Let's see if we can do it. So if I do this, X is not a type object. Yeah, so now self.wirEdge returns a byte, but that's got a value of 4. So if I do 4 plus... Yeah! This isn't dodgy at all. Alright. Return super. Right, so if I do that now, does this still return 8? Yeah. Self.wirEdge plus equals 1. Self.wirEdge. And this should now equal 9, yeah. So far so good. Dodgy things working well. So this will return a new int, is my thought. The default implementation. So if we come in and check this out, self.wirEdge plus equals 1. So the new thing should equal, yeah, so my value should equal 4, and the new value should equal 5, yeah. And is new value an int? new value is an int. Yeah, okay, so if new value is greater than equal to greater than 255, but we want to cast it and turn it into a byte. Can I do that? No. New byte is 5. Return new byte. Now this I think this is fine. I'm just going to do some dodgy stuff. If new byte is greater than 255, new byte minus equal 256. New byte is less than 0. New byte plus equal 256. So now when I come down to here, it should work. But if I made this 256 and then I added 258, when I get to here, self.yreg should equal 0, yep. And when I add 258, self.yreg should equal like 3 or something. No, so now it doesn't equal. So, where am I at? CPU. Okay, plus equals 258. So shouldn't that hit? CPU.yreg is now... okay. Holy shit. In new byte would be an int, not a byte, wouldn't it? Correct? Track off. That is true. So I want it to be I want to create it. Holy shit. Yeah, so let's presume that if it's the first time that I'm creating it, it's not going to be invalid. That's not a valid assumption though. Wait, if I define sub on this, is this going to work? New byte is a byte that equals 0. Return self new byte, yeah. New byte plus equals 258. Well, that works, but I get the feeling I'm doing a lot of things that I don't need to be doing. So I get the new byte. Yeah, because this is still returning an int. I really want this to return a byte. Yeah. Because I'm creating one every time. Shit. So byte new byte would just be the easier way to do it. Well, would be ways that adjust. Oh, right, okay, sorry. Forget I said anything. Yeah, the problem is this thing is going to return another call of this, and the only reason it doesn't go recursive is because it doesn't hit these if statements. Not like this, indeed. Yeah, this sucks. Yeah, fuck that. Okay, let's just do it then. Return that. I really don't need that to do anything. Let's just do if we have an add. If new byte is greater than 256. Boom. Yeah, new value. Cool. Nice. If you don't simplify stuff, it doesn't seem simpler. Yeah, that's true. But on the other hand, whatever. Basically, it'll just overwrite. This just does. The other way of doing this would just be turning these into properties, like creating accessor properties and stuff. But whatever. It's just going to give us some basic overflow detection for our registers. It just means that we can do that. For plus equals, there's a special underscore method to speed up. Ah, shit, are you serious? Okay. Alright, alright. You've convinced me. I will come back to it one day. Where are we up to? Cool. In X, P match and the X max are wrong. So what's my X reg? 256. Yeah, that would be bad. Yep, that'll do it. Alright. Instruction not found, AA. Alright, let's keep going then. A8. Tay. Alright, so that's going to come back to here, and this is these things we never finished off doing. So transfer A to X, so tax is going to be implicit with a register modifier. Let me just copy this one actually. Dun, dun, dun. Tax is going to be AA, and we're going to transfer A to X, so CPU dot xreg equals CPU dot areg. Return the xreg, then txa is going to be the same but opposite. So the areg is going to equal the xreg, and we're going to return the areg, then A to Y, so on. So TAY is going to be 8A, transfer A to Y. So the Y reg is going to be what we equal, and the A reg is going to be what we take it from, and then the last one's going to be transfer Y to A, which is going to be 9, 8. So the A reg is going to equal the X reg. Nope. So Y to A. A reg is going to equal the Y reg. Return the A reg. Cool. Done. Invalid operand for TSX. Return cpu.xreg. Store x absolute. Another option is to define xy as int constants, then do regs byte array 0, 0, define them as, yeah. That's true. That's true. It's fine, I guess. Definitely the easiest way of doing it would be adding on accessor properties in the CPU, which I may as well do now. I kind of wanted to come up with a cooler way of doing it, but you know, that's life. So it would be def because you can then do sets and things with this. Byte array is faster. Yeah, I'm not too concerned about speed yet. I just want to make it work. That's life there. Here we go. Property. Nope. Come on. Yeah, it goes and says it's right. Java XY. Here we go. Yeah, so we could just set our xreg like this. Property accessor is not created. Yep, so and then we can do our checks in here. Soft.xreg. Yeah, okay, let's do it this way. Done. And now returning the xreg. Return that and setting the xreg. Yeah, so this would be an example of how you would do it. Yeah, so you could do it that way as well. Which is kind of annoying because you have to do it for everyone. but let's do it. It's going to save us time in the long run. You're right. Underscore. Could always just use NumPy. Really, does NumPy have a divide type? That would save me a load of time. It's fantastic. What is my virtual environment called? Oops, I was having that on this monitor. So let's look up NumPy and how we do it. Import NumPy as NumPy, and we actually want this to be 1, I presume. So if we use, yeah, there's better things. NPy dot int 8. I believe that's what we want. Yep, so now dt is an int 8. So how do we... Sorry, wrong browser. NumPy byte. U and 8. Yeah, we do want uint, don't we? In other cases, we might want ints. Potentially. Yeah, okay, so yep, so numpy.uint8 of 1. Set this shit up. Cool. 255. 256. Ripper. Yeah, how's it going? Emendero, very good. I've stopped trying to roll my own byte implementation, and this is a much nicer way of doing it. Cool. Let's just do that then. Zero. Sick. So now all this shit can go. Nice. Still have to catch the overflows. Do we for Reg's? Good job. Need to go to work now. Thanks, Emulator. We do for when we're computing results and stuff. Do we need to catch them for the Reg's though? Let us see. Meant to carry when it's needed. Yeah. But that's handled in other places, I think. Unless this is why this is wrong. In which case you would be right. Pay match. And CPU.statusreg.toInt 2 carry bit. Cause yeah, you're right. Oh god. How did I even do that in the past? How the hell? Because these things would have prevented that. This would have set it to 0, right? So what's the instruction? It's a binary. What's the actual instruction? An I and Y. So what's the Y reg? Ah, right, they don't actually match. 256. Lol. Right. So when I do a plus, do I need to add? Add another number. Yeah, this is probably what it's going to have to be, right? Nope. NES test. So that's CPU. Okay, let's go to here. Self.xreg. Yeah, okay. It now becomes a UN64. Okay. Whereas if I did that, I'd be willing to bet that. So I'll just cast to the higher type. Yep. Okay. Oh, bloody hell. Nope. Somehow this still happened. Jesus. Okay, so something else is modifying the Y reg at some other point. Y reg, find usages. Value rights. Nothing. And instructions, alright. LDY. Okay. Right, how about that? Hey, okay, we got past that. That works. Alright, TSX. TSX is broken. Why? Everything is broken. Holy shit. X match. Alright. And what's the actual one? cp.xreg. 9. What have we done at TSX? Wait a minute, self.expected x. TSX. What does the TSX instruction mean? Transfer stack pointer to index x. Alright, let's find where we implemented TSX. Alright, let's try that. Shit. So, x does not match. SP does not match. CPU does not match. So this could just be our TSX is actually broken rather than anything that we're doing here. CPU.xreg. Pull data. What's that pull data? 9. We expect this to be 251 or something. The pull data should be the stack pointer. TSX is literally transfer the stack pointer to x. Not. Huh. Yeah, so not pull something from the stack. Yeah, okay, shit. So that's just this instruction being wrong. So TSX is just an instruction. Which sets the negative and the 0, the bytes. And then we just want it to do a write. Want to get the SP reg. And then we kind of want the same thing to happen at TXS. Write, which we just want white. Which we just want to return the CPU.x reg. Wait a minute, transfer x to the stack pointer. What does the stack push do? Gets the data, write the data to the stack, increases the size of the stack. We actually just want to set that, I believe. TXS, and then where's TSX? Yeah, we don't need it to be that. Now, so the stack pointer reg always is 0xFD. I believe that the stack pointer is always going to be in a UN8. Therefore, this is fine. Empire.uint8. And do I set the memory CPU equals return. Yeah, perfect. Okay. So that should work. So basically, our stack pointer should always be UN8. NumPy has no attribute UN8. Unit 8. Yeah, alright, rock on. Cool. TXS, still wrong. But it looks like everything is right except the P match, which is a lot better. So, what's wrong? Oh, shit. What am I using? Only 255 byte stack. Yeah, I'm pretty sure. Seeing as how it starts at 0xFD and you count down, yeah, I'm pretty sure the stack is only 255 bytes. Maybe I'm wrong. Memory map, not really. Registers is what I wanted. I think the stack pointer is only 200. S is byte wide, yeah. Alright, what's different about these? 111, the topmost bit is meant to be set, but it's not, which is the negative bit. So what's this? Transfer X to stack. So what's my stack pointer? 105. Yes. So I guess the stack is just probably your first 256 bytes in your RAM, I guess. I don't know. So SP_reg is 105. This is what we expect it to be. Yep. So we expect it to be negative. So let's go TXS. Let's find that again. Is it TXS? Alright, TXS. So the CPU reg. So our SP reg is 105 now. How big is the NES memory? So that's what this NES memory map is, but the basic answer is there's 2 kilobytes of RAM here. Then the next, so the first 8 kilobytes is really just mapping to the first 2 kilobytes of RAM. So this is just so you don't have to calculate the most significant bit. So this will point back to this. And then you have another 8 kilobytes of, you know, random stuff. So access to the PPU, access to the APU, and then basically you load your cartridge in is most of the bottom 8 kilobytes. So the only thing that's not a byte wide is your program counter, because that's going to be a 16-bit value. So you have a 16-bit address bus where you, you basically, half of it is just mapping to 2 kilobytes of RAM, and the other half of it is mainly where you load your cartridge in, essentially, as well as some other register stuff. But CPU.spreg. So how is that meant to be negative? Bam, 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 bam. Bam, bam. So if the 0 bit, and what am I talking about? The negative bit. Does it set the negative bit? Yes. Yeah, this is false, because it's not 0. I mean, it's not negative. Value is just 105. So why the hell? Expected SP reg. Alright, so TXS. X goes to the stack pointer. Yeah, the stack is always on page 1. Okay, so it's actually stored from 100 to 1FF and works top down. Cool. So I'm not quite sure. I presume this should return SP. I mean, what's X? It should be the same, right? So how is this a negative? Let's look at the NES test log. up to the very top, TXS. So this is where we're up to, presumably. Yep, so here we've got a value on X of 69 and the stack pointers to FB. So TXS transfers that value to the SP and sets a P of E4. I think this is going to be our problem, presumably. 1, 1, 1, 1, 1, 1. It's actually not setting. It's not setting the negative flag. It's just leaving it from what it was at before. So TXS doesn't actually set the negative flag. Is what it looks like. Maybe I'm wrong about that. But I get the feeling that according to NES test ROM, that TXS doesn't set the negative bit. What happens if I do this now? Yeah, then we keep going. Alright. So what's wrong here? P match and A match. Load A absolute. Alright, so what's the self.expected A? And what's the actual A? 0. So what does load A do? Load A. Load accumulator with memory. So memory to A. So expected to put in 51 and the actual value is 0. So where's load A? And it will be in load instructions, load A. So CPU.areg, how many of these do I find? A lot. We do a lot of load A's. This is interesting. Holy shit, okay. Oh, there we go. Load A, absolute. Oops. We wanted the memory address. Let's cut this out. Let's find out what memory address we expected. Do we have access to the instruction? Right, okay. Self.instruction? Nope. Okay. So our A is different. Our A is 0. ADC type. And arithmetic based load. Load operation. Load instructions, base instructions, load A. Yeah, so this is eventually gonna... What is going on? So what's the value that we're loading? Where am I up to? Okay. NES test log. Yep, here. So we want to go to memory location 0180. So let's go to our base instructions. Let's chuck a breakpoint in here. When memory address equals that. So memory address equals 384. The value equals 0. So why does the value equal 0? So let's copy this breakpoint, take it off, and let's put it here. Let's go. Okay. Just going to be doing some dodgy debugging. This is going to be the last thing I do before I head off. Just want to try and fix this last bug. cp.getMemory. Yep, so let's step in. Who owns this memory location? The RAM owns it. We're getting one size back. Self.getMemory is 0. Right. Self.memory start location is 0. So at position 384, the memory is 0. Yeah, okay. So do we see this memory value being written anywhere else? No, so when we load from 0180, so A already equals 33 everywhere before this. Let's just check that load A, load accumulator with memory to A. So it thinks that storing whatever's at 180 already equals 33. So this operation should do nothing except change the status reg flags. Oh shit. You know why, I reckon? What's hex 180? Yeah, so this is what we were thinking about earlier, was that... Where the hell was... Talking about the stack. S is somewhere, the memory map. 0x. There's something I saw where it started at 0x100. I'm pretty sure. With the 6502, the stack is always at page 1 and works top down. So the stack actually exists in memory. Well, I mean, obviously the stack exists in memory, but the stack exists in memory at 100 to 1FF. Where do I store the stack at the moment? How do I even implement the stack? fuck? Stack pointer 0xFD. Yeah, I don't know. That's the problem. Anyway, thanks for watching. I'm gonna wrap it up and head off. It's been 4 hours, Jesus. Oh, I feel like I've got a lot done though. A lot of stuff I didn't get done. Bit of wasted time on all the byte stuff, but how many instructions do we have now? Oh. We have... yeah, 121. So we made it to 120. Which is pretty good. Have a nice day. Thank you, Overx. I'm gonna go to the gym. Which is very nice. So, yeah, thanks for watching. I don't know when I'll next stream, but for those of you following today and following at home, thanks for doing it. Thanks particularly for Overx for following along and giving some good advice today. I think and Danny for dropping by and doing the same thing. SP should start at 0x100. Thanks, stream. Thank you, Sigma. Should start at... yeah, that's what I thought, because that's what this seems to be saying, was that the stack is always on page 1. But I'm pretty sure if I go back to here, and I go to power up state, oh, so the stack pointer is set to FD, but I think it's actually stored. The stack is always on page 1. It's actually going to be stored here. So even when the pointer is FD, that actually means 1 FD, where it is mapped to in physical memory. I have no idea why that would be. I guess because they want the stack pointer to store in 1 byte. So we're going to need to do some funky byte. Yeah. So anything that refers to the stack pointer should actually just be added by 100. Anyway, figure it out another day. Thanks very much for coming along. Thank you, Sigma. Thank you, Overx. Thank you, Danny. And yeah, I'll see you all next time.